Hello everyone, this is Algebra 1, Lesson 6-3. Here, exponential growth and decay. In this lesson, we'll use exponential functions to model situations and make predictions. Some key vocabularies in this lesson would be compound interest, decay factor, exponential decay, exponential growth, and growth factor. Let's start with exploring reasoning. Cindy is buying a new car and wants to learn how the value of her car will change over time. Insurance actuaries predict the future value of cars using depreciation functions. One such function is applied to the car whose declining value is shown at the right. So as soon as you buy the car, which may be $10,000, after a year, the value drops to $8,520. And then after another year, it drops to $7,213. And then the next year, $6,100. And then the next year, $5,210. So let's describe how the value of the car decreases from year to year. First of all, how much did it actually decrease every year? Do we have a linear function or an exponential relationship is what we're trying to figure it out. So from 10,000, we're going to subtract 8,520. And that's $1,480 of decrease. And that's approximately how much percent from the original? About 15% decrease, okay? And then from 8,520 to 7,213, the value dropped by negative 1,307, okay? And that's also about 15%, okay? And then from 7,213 minus 6,100, the price dropped another 1,113. And then the next year, it dropped $890, which was also about 15% of the car value before in the previous year. Okay, so how can we describe the value of the car? How much it is decreasing? Like the amount of decrease every year. Is it increasing or decreasing? This is amount of decrease of value each year. They're dropping, right? So you can also say, part A, the differences between the car's values are decreasing as time after purchase increases. Make that a red. Okay, so what kind of function would explain this type of pattern? Is it a linear function or an exponential function? It is an exponential function. Given your answer to part B, what is needed to find a function the actuary is using? What did we learn about exponential function last time? we need to have a common ratio between the values of the car consecutive years and the starting value of the car. Okay, these are the two values that we actually need in order to write the exponential function equation. Okay, so think about what kinds of situations could be modeled with exponential growth or exponential decay functions. Let's look at example 1. Exponential growth. The population of Hillsville grows at an annual rate of 15%. What will the estimated population of Hillsville be in 5 years? So right now, it says, welcome to Hillsville. Its population is 5,000. 5,000 people live here. And if it grows 15% every year, that means you're going to multiply in order to get how much total the people are next year. What do? 5,000 is the whole, right? This is 100% right now. But we're going to multiply by 115% to get what is 115% of 5,000, right? So 115% in decimal is 1.15. So if you multiply that, you'll get the total of the next year. Next year's population, right? But how do we write an equation that does this every year? And your initial value is 5,000. You're going to use the exponential function. Exponential function f of x, where you have a, your rate, the common ratio, and then b, the base, which is, b is the common ratio, sorry, and a is your initial value, right? Initial value. And b is the common ratio, okay? But then your base here, your ratio increases 15% every year. So you're going to multiply 115% every year. So you're going to add 0.15 and say our function is going to be 1 plus 0.15 times 5,000. And so the function is actually f of x is equal to 5,000, your initial value. And then 1.15, the common ratio. How much is it increasing? If you just put 15% instead of 115%, what do you get? You get the 15% of the population next year. That means you don't have a population increase. That's actually a population decrease of 85%. So you need to include 100% so that you're adding 15% from your previous population, okay? So that's a very common mistake. So please be careful. Let's look at the next page. So after you write the function, which was initial value times the common ratio to the x power, right? You find the expected population in 5 years, which means you're going to plug in 5 for x. And you get 1.15 to the power of 5 times 5,000, and that's about 10,056.79 people. So in 5 years, we can say that the population is expected to be about 10,057 people. Okay. So let's look at try number 1. The population of Valleytown is also 5,000, with an annual increase of 1,000. Can the expected population for Valleytown be modeled with an exponential growth function? Explain. So right now, the population is 5,000 for Valleytown. Okay. So right now is 0, right? And then after 1 year, it's going to increase 1,000. Then after another year, it's also going to increase by 1,000. So every year, it's going to increase by 1,000. Is this an exponential function? No, graph it. You're going to get, if this is 5,000, you're going to get a graph that looks like this. 6,000, 7,000, 8,000. It's not an exponential function, okay? This one is going to look like this, but this one is a linear function. Okay, so the growth, it only adds 1,000 every year. Your growth does not increase over time or decrease over time. That means it's a linear function. So no, the growth is linear because the population increases by a constant value, 1,000 each year. Does that make sense? Yes. Okay, so let's think about this concept. We have something called an interest in a bank. So interest is calculated in two ways. You have a simple interest and compound interest. Simple interest is interest paid only on the principal. Okay, and then compound interest is the interest that's paid both on the principal and on the interest that has already been paid. What does that mean? So if you get an interest this year, and if you get a simple interest, that means your interest is going to be the same every year. You're going to get a fixed amount of interest. Okay, but then compound interest, if you have a compound interest, then whatever interest you have, that's also your money now. So next year's interest is going to be a little bit more because it includes the interest in your initial money. Okay, so the interest, the compound interest also gives you interest on the interest that you already got paid in previous years. Okay, so the compound interest formula is an exponential growth function. This is a compound interest formula. Simple interest is not an exponential function because you have a fixed interest, okay? So compound interest formula could be represented by this equation. A, where the amount paid in total would be equal to P, principal amount, so your initial amount, times, parentheses, 1, this represents 100%, plus the rate, R, rate of interest, over N, the number of times per year the interest is compounded. So every year you might get just 1 time of interest or 2 times of interest per year and so on. And then all of that to the power of N, the number of times the year the interest is compounded, times time in years. Okay? So every year you get the interest, and the first year you just get an interest from your principal amount, but then the next year you get the interest of your principal amount plus your rate, your interest that you got paid last year. Okay, so this is the graph that shows $10 at 5% simple interest, which is a linear function, and 5% interest compounded quarterly, so every quarter. So here, now is a good time to go over the vocabularies that we're going to see. So if you get interest yearly, then that means how many times do you get paid every year? Once. If you get an interest yearly, then you just get 1 interest every year. Okay. If you get a semester interest, if you get an interest half a year, okay, semester, every semester, or half year, okay, then that means you get paid twice every year. If you get quarterly interest, then you get interest paid 4 times every year. Okay, you get a monthly interest. Every year you get paid. That means how many times do you get paid in a year? 12 times. Okay, so these are important vocabularies that you need to know in order to understand How many times do I get paid in this problem? All right, let's look at the next page. Example 2, exponential models of growth. Kimberly's family invested in a certificate of deposit, CD, for her when she was born. The interest is compounded quarterly. That means 4 times every year. Okay, so they deposited $3,000. That's your initial amount. P, your principal amount. Annual interest is 8%. So rate in decimal is 0.08. Okay, and then interest compounded quarterly. That means your N is 4. So use the equation of compound interest formula and plug in what you know. A is equal to principal P, 3,000 times 1 plus 1 is always going to be 1. Okay, R 0.08 over N to the power of N T, and T could be just T. And then you simplify that, is going to be your formula. Okay, but then if you want to solve for the problem, what is the value of the CD at the end of 5 years? That means you're going to plug in T is equal to 5. And then you'll get your answer in 5 years. So 4 times 5 is 20. So you do 1 plus 0.08 divided by 4, which is going to be 1.02 to the power of 20 times 3,000. You're going to get about 4,457.84. So your answer is about $4,487.84. Okay, that was part A. In part B, will the value of Kimberly's CD be greater after 15 years if it's compounded annually rather than quarterly? So you can compare the exponential function you found in part A with an annual compounding or the same 15 years. So if you get paid quarterly, that means your N is 4. So 10 times that by 10, when T is 15, then you get 9,843.09. If you get paid every year, that means your N is just 1. So 3,000 times 1 plus 0.08 is just 1.08. Okay, it looks like your rate is greater annually, right? To the power of 15. But you actually get less money in 15 years by several $100s because why? Why would this be less money than quarterly? Then, it's because over time, over a long period of time, if you get paid interest 4 times every year rather than once every year, you get paid interest from your interest. So even if your principal amount is the same, and your rate looks like it's smaller, you're still gonna get more money paid quarterly than annually because your actual rate is still the same, 0.08, right? But it looks like it's smaller because you didn't divide it by N. Okay, so the value of Kimberly's CD will be less if the interest is compounded annually rather than quarterly. So let's look at try number 2. A, what will be the difference after 15 years if the interest is compounded semi-annually? Oh, yeah, so that means this also means twice when N is twice, okay, rather than quarterly. And then what will be the difference after 15 years if interest is compounded monthly? So this is when N is equal to 12 rather than quarterly, 4. Okay, see if you can do it by yourself and come back when you're ready for answers. And let's add semi-annually in our previous notes here. Okay, are you ready? So part A, What's the difference after 15 years if the interest is compounded semi-annually rather than quarterly? So we already know the quarterly amount after 15 years, okay? So quarterly, you have 9,843.09. But then if you have semi-annually, that means your equation is 3,000 times 0.08 divided by 2 to the power of 2t. So you're gonna have 0.04 to the power of 2 times 15. And to the power of 30. So 3,000 times 0.04 to the power of 30 or 0.04 to the power of 30. Oh, right. It's not 0. I'm sorry. I forgot the 1. You need to add 1. Very common mistake. Okay. 3,000 times 1.04 to the power of 30 is gonna be about 9,730.19253. So you're gonna subtract quarterly minus semi-annually in 15 years. Okay, so 9843.09 minus 9730.19 is $112.9. And that is your answer. Okay. So there will be $112.9 less in the account if the interest is compounded semi-annually. So what will be the difference after 15 years if the interest is compounded monthly rather than quarterly? So let's figure out monthly now. So monthly is 3,000 times 1 plus 0.08 divided by 12 to the power of 12t. So that's 3,000 times times, so let's make this in fractions because 0.08 divided by 12 is a small number. Okay, and then 12 times 15 is 180. Wait. I don't think I did the math right. This one is just 151 over 150 to the power of 180, okay? So that's gonna be about 5,104.77158. So we're gonna subtract monthly minus quarterly. So this minus 9,800. Are we sure? Wait, 3,000 times 1 plus 0.08 divided by 12 to the power of 30. Right, to the power of 180. I forgot. is 9,000 actually. I'm sorry. 9,920.764432. So minus 9,843.09 is going to be about $77.67. So there will be 77.67 more counted to interest is compounded monthly. Okay, here we go. And there will be $112.9 less if the account if in the account if the interest is compounded semi-annually. Okay, so we've basically figured out all the possible ways you could have interest in 15 years if you start with a $3,000 and you get an interest rate of 8.88%. Okay, so it really depends how many times you get the interest, especially in the compound interest formula. So let's look at example 3, exponential decay. A video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases by 25% each day after that. In how many days total will the video stop being a fan favorite? So the requirement is that it needs to receive at least 1,000 views per day. And so the question, in how many days total will the video stop being a fan favorite, which means when will it go down under 1,000 views, okay? So starting from 8,192 views, every day it decreases by 25%. So after a day, it will be 6,144. After another day, it'll be 4,608. Then after another day is 3,456, and so on. This is an exponential decay function because it decreases exponentially. Okay, so this is another type of exponential function where it decreases exponentially. It's not a linear function, but it decreases, and it's also an exponential function. So your growth function looks like this, right? When x gets bigger, your y also gets bigger. But then your growth, compared to your growth, your decay function goes down. Your y values go down as x goes up. Okay? So the decay function is very similar to the growth function. Your growth function was f of x equals a times 1 plus r over, well, that was the compound interest formula. But the general growth function is 1 plus r to the power of x. Okay, but then your decay function is function of x equals a times 1 minus r to the power of x. Okay, where r is the decay rate. So step 1, you're going to model the situation. It starts with 8,192, and then it decreases by 25%. So that's your rate, 25%, which is 0.25 in decimal. And so 1 minus 0.25 is 0.75 is what's going to be left. 75% is going to be left over after every year. Okay, so you're going to write the equation to find x if f of x is equal to 1,000. That means you do not have to plug in any number in x. That's what you're trying to get. How many days after would you get 1,000? So f of x is 1,000. So you put 1,000 is equal to 8,192 times 0.75. How do we figure out x? You can estimate the solution. Let's go to Desmos.com. So go to Desmos.com, plug in your function, 8,192 times 1 minus 0.25, which is 0.75, to the power of x. And how do we see this? You can zoom fit, or you can change your axis. Your y-axis seems to be very big, right? So you can do 10,000. All right, 10,000 over here. There you go. Then you start with 8,000 something, right? And then you want to find the line where it hits 1,000, right? So your 1,000 line is over here. So put another line. That's when y is equal to 1,000. So your intersection point is 7.311, 1,000. That means after 7.311 days, the views are going to be exactly 1,000. Okay, so what does that mean? 7.311 days. After how many days would it be below favorite? So the video will stop being a fan favorite in 8 days. If it's 7, it's still over 1,000. So it's still gonna be a fan favorite. But then the 8th day, it's gonna be not on the list. So the answer is 8 days. Okay, let's look at try number 3. Suppose the number of views decreases by 20% per day. In how many days will the number of views per day be less than 1,000? So it's the same kind of problem, but instead of 25%, it decreases by 20%. So now we have a different rate. So your new function should be 8,192 times 1 minus 0.2 to the power of x instead of 0.25. So then that's not 0.75. What is it? It is 0.8 to the x. So let's put that down. We're gonna erase this for now. And then put a new function. F of x is equal to 8,192 times 0.8 to the power of x. And we still want another line that says y is equal to 1,000, okay? And then this is your intersection point, 9.425 days, 1,000 views. So after 9 days, after 9 days, would it be a fan favorite? Yeah, after 9 days, it's still a fan favorite. But then after 10 days, it is no longer going to be a fan favorite. So if it decreases 20% per day instead of 25, the video will stop being a fan favorite in 10 days. Okay. All right, let's look at the next page. Example 4, exponential models of decay. The number of pica in a region is decreasing. How does the decrease in the pica population for years 1 to 5 compare to the population for years 6 to 10? Pica population are decreasing by 8% each year. The initial population is 144 picas. So write an exponential decay function to model the situation. So your initial value is 144. 1 minus 0.08 because it decreases by 8% each year to the power of x would be your decay function. We're going to compare years 1 to 5 and 6 to 10. So we're going to find the number of the population after a year. So plug in f is equal to, when x is equal to 1, f of x is equal to 1. when x is equal to 1. So f of 1 is going to be about 132. Okay, 144 times 0.92 to the power of 1 is just 0.92. So 0.92 times 144 is about 132. And f of 5, when you plug in 5, is 95. So that means your slope is your rate of change in between year 1 and year 5 is a decrease of 9.25. But then from year 6 to year 10, year 6 is 87, year 10 would be about 63. So if you subtract, so where is this slope coming from? Where is this slope coming from? Remember your slope equation, y is equal to y sub 2 minus y sub 1, and x sub 2 minus x sub 1, where you have 2 points where the first point is x sub 1 and y sub 1. Your second point is x sub 2 and y sub 2. Okay, so use the slope formula to figure out your slope. Your rate of decrease is negative 9.25 for year 1 to 5 and negative 6 for year 6 to 10. So we can compare them. For years 6 to 10, it decreases by average of 6 picos per year. But for years 1 to 5, it decreases by an average of 9.25 picos per year. The average rate of change for the pico population decreases as years increase. Okay? This is how you can put it into words. So let's look at number 4. How would the average rate of change over the same intervals be affected if the population increased at a rate of 8? It increased instead of decreasing, okay? So your new function should be a growth function, right? F of x is equal to 144, the initial one, but then 1 plus 0.08 would be our function. So instead of 0.92, we have 1.08 to the power of x. Okay, and then plug that in. Let's hide these. F of x is equal to 144 times 1.08 to the power of x. Wait, 144 here. 1.08 to the power of x. There you go. Okay, I'm gonna decrease the value of the x-axis. Let's do 200. There you go. And then we have the population. And what do we want? So years 1. Let's look at year 1. Year 1 is it's about 156 pico. So f of 1 is about 166. I already forgot. 156. And then f of 5 would be about, when x is 5, you get 212, about 212. Okay, so find the rate of change for that one. Your slope is 212 minus 156 over 5 minus 1. Okay, for years 1 to 5. Then years 6 to 10. F of 6 is about 229. And f of 10 is about 311. Okay, and so your slope of this is going to be 311 minus 229 over 10 minus 6. Okay, so what do you get? So for the first slope, 212 minus 156 is 56 over 4 is 14. Okay, 311 minus 229 is 82 over 4 is 20.5. So what can we say? How does it change? The average rate of change for years 1 through 5 is 14. And the average rate of change for years 6 through 10 is 20.5. So what can you say? The average rate of change increases as years increase. Okay. All right, let's look at example 5, exponential growth and decay. Rich is comparing the cost of maintaining his car with the depreciating value of the car. When will the cost and the value be the same? So the value starts at $20,000 and decreases by 15% per year. That's the decrease. That's the decay function, right? And the maintenance cost is 500 the first year, and then increases by 28% per year. Yeah. So this is the growth function. And you can write exponential functions using these two equations. Notice that they're writing 20K as 20 and then 500 as 0.5K. Okay, so this is in terms of thousands, the y values. Okay, so your function is 20 times 0.85 to the power of x and 0.5 times 1.28 to the power of x. Okay, and we want to figure out the solution, which is when the cost and the value are the same. So this intersection point. So graph two equations in decimals. I'm going to hide that as well. Now I'm going to graph f of x. It's going to be 20 times 0.85 to the power of x. And then g of x is going to be 0.5 times 1.28 to the power of x. Okay, and we want to figure out the intersection point, which is 9.011, 4.624. And that's when the cost is the same. The cost of maintenance are both about 4K and 624. So about 4,500, they estimated down by a lot at 9 years. Okay, that's the solution. So look at try it, explain how to use tables on the graphing calculator to answer this question. So you can use tables. If this is y, and that's y, you can create tables in decimals. Go to settings, and you can change that to tables. You can also change that to a table as well. okay? And then you can plug in the numbers here. 9 after 9 years. And then you can see if the numbers get closer and closer. And yeah, that's how you can see, oh yeah, in about 9 years, their cost is going to be the same. Okay, so how can we explain that? You can say, you can type in both equations in decimals. Then go to settings, then click the table to make the tables for the two functions. I can't really see. Okay. Then you can type in the x values to see when their y values are. Okay. So you can try to write in your own words. You can copy mine down. There you go. Okay, but the whole goal is to find the intersection point. All right, so let's summarize this lesson, exponential growth and decay. We learned that the exponential growth grows. It grows exponentially. It increases, the y values increase as x values increase. The exponential decay function, the y values decrease exponentially as the x values increase. And the compound interest function starts with an initial value and it compounds the interest every time. So the periods per year is very important. Principal is the initial value. The annual interest rate is the rate. Okay, so these, please keep in mind for these equations, these are very important. All right, that was lesson 3, exponential growth and decay. We'll continue with the next lesson. Lesson 4 is about geometric sequences. And so that's going to be a little bit different, but it also has to do with exponential functions. So I'll see you in the next video. Thanks for watching. If you have any more questions, please feel free to ask Ms. Kang in class. Bye.